We have seen by this time what a category is, what a functor is, what a natural transformation is. Today we shall look into another example of a category, and it will be instructive to look into this by seeing the several kinds of examples that this category actually presents itself as a general case of. So suppose we have two functors and the category we shall write as this. This is the category of F over G. What are its objects? The objects are triples. Where A is an object of A, B is an object of B, and F is a morphism from FA to GB. In other words, looking diagrammatically, the objects look like this. Now, what would be the morphisms? So we would like a morphism from here to here. So we have another object over here. And we are going to search for a morphism. A very useful tool in category theory excuse me, is to complete the diagram. So to complete this diagram, we would obviously be thinking of morphisms of C like this. Well, why not the other way around? That means one going up and the other going down. Well, it seems that such asymmetric things are often very not very natural in general, right? So we should not be thinking about special things. So without any particular condition, just completing the diagram should mean arrows in the same direction. So now, what would be these arrows? These could be any arrows of C, but then giving any arrows of C doesn't make it very different from the arrow category of C, which we have already seen. So these arrows must be morphisms of C which are images. That means it should be a pair where U is a morphism in A, V is a morphism in B, and obviously this diagram commutes, so GV composed F is G composed Fu. So that means I will need this thing like this. Observe, see, I have always emphasized the need of some kind of diagram calculus or whatever. See, in trying to remember this, it is this pair, and how do you get it? So again, there is some kind of a cross multiplication rule. So G composed Fu, and then you come to this, it is this one will be GV composed F. Okay, so that's the rule. Okay, so this is my composition. Well, once we have defined this composition, it seems that the most natural this morphism, we must obviously think of compositions being defined point-wise, coordinate-wise. So if I have a third object, say and we have this as F P and an F GQ, then we automatically sorry, this was this. Then we automatically see that this is F of Pu, and this part is G of Q. Okay, so that means if P the composite is Pu and Q, and hence the identity should be 1A, 1. Okay, so over here if we have this is this direction. Okay, and this makes a category. So this makes a category. Okay. Now, the first thing to observe over here is what are the objects of this? Well, I need to give an object of A and an object of B, and there is some set over here. And what is this? It is exactly each one such is given by a morphism from FA to GB as you take. So this is actually equal to A in A naught. Okay. So that's mine. And then what are the morphisms? Well, this is pairs of morphisms which are images. So it is actually let's see, a subset, or let's see like this, yes, it's a subset of F image of an image. So F of F and G of G, such that F is a morphism of this and G is a morphism of this. So it turns out that if A and B are small categories, so also is this. And I leave it to you to answer this question. And the idea is, we are looking into images. Now, let us look into, remember, a functor is a pair of functions. The object part function and the image part function. Good. Now, suppose I have a small category. That means there is only a small set of morphisms. If I define a functor on this, however big may the domain category be, how many images can be there? Well, if I look into the functor part of this, then if that functor part is an injection, that's the largest size of the image. For if it is not an injection, some of things would actually be clubbed. So the largest size is same as that of the number of morphisms in the domain. So given any functor from a small category, whatever the codomain category be, the image morphisms will still be a small set. So if A and B are small, this pair is, this set of all these pairs cannot be other than small. So that's the rough idea, but you have to justify it. So that's why I keep it open. Okay, so that's the first part of the story. Alright. Now, if we look into this diagram, this is very, very suggestive. Why? Suppose if we look into this, say this left side, we have on this left side, we closed it. Sorry, so let me just try it. This left side is completely controlled by the category A. What about the right side? Let's take another picture on the right side. The right side is completely controlled by B. Yeah? It's completely controlled by B. And there is still a third one, which is the, say let's take this middle. Okay? So this side is completely controlled by A. This side is completely controlled by B, okay? And if we look into this side and how we have defined the morphisms, this side is completely controlled by the arrow category of C. So we have three functors. And we have three functors. Okay. What does P0 do? P0 takes FB to A. Okay. It takes CGD to C, and a morphism it just takes to E. Okay. P2 on the other hand takes to B, and the morphism this is taken V. And what does P1 do? Well, it takes to the middle one, which is the morphism of C. This it takes to G, and UV it takes to FU and GV. That's exactly a morphism of C. I should have written this, sorry. Obviously there are these domain and codomain morphisms coming over here, and we have this two functors, and how we have defined it automatically tells us that FP0 is partial 0 P1 and G P2 is partial 1. So this commutes. Not only does this commute, but this commuting is quite universal. Let's see it again. So, let me copy this diagram. And suppose we have another category, say X, and we have a functor, say T0, T1, T2 and T1, such that ft0 is partial 0 t1 and gt2 is partial 1 t1. Okay. So now let us have a look into this functor t1. That's really the interesting one. Okay. So this goes to the arrow category over here. So it takes an object and produces a morphism of C. So this is a morphism of C. Okay. So a morphism will have a domain. So what's the domain? I need this space. So what's the domain? That's the domain of T1x. But see, this is same as f of T0x. And similarly, the codomain of the morphism T1x is G of T2x. So this domain is f of T1x and this is G of T2x. Remember, T1x and T1 and T2 are also functors. Good. So if we have another object y, the picture is almost similar. So we have f of T1y, g of T2y, and this is my morphism T1y. Okay. And now what happens to an image? So this is going to be a pair. Okay. This is going to be a pair. So this is this pair. Now, I don't know, this is the arrow category. So U and V are arbitrary arrows. Okay, of C. Let's again utilize the fact that we have these two equations, ft0 and gt. So what is U? In the arrow category, if I look, which is a morphism of arrow category, U is nothing else but the partial 0 of uv. But that is partial 0 of t1 of f. But then I know this is nothing else but f t0f. So u is f t0f, and similarly v is this, which is partial 1 of t1f. So this is g of t2f. So your u becomes t1f, and this becomes t2f. So this is nothing else. So this is nothing else, but I can write now as t1f. T0f and T0f. I made a mistake over here. This is T0 and this is also T0. So this is T0f and T2f. Okay. So uv is nothing else but T0f and T2f. So observe now what we have. So therefore I have, if I rewrite this, what do I get? So T0x, T1x and T2x is actually an object of f upon g. And moreover, what does this say? T0f, by my definition, is a morphism of A. I made another small mistake. This is ft0. This is ft0, and this is I was a little bit. So, okay. So T0f is a morphism of A and T2f is a morphism of so this is also wrong. Yes, I was a little bit fast. So this is f T0f and g T2f. So what I was trying to say is you have and T2y over here. So this is also in an object, and this is T0f and T2f. This is now a valid morphism of this. So therefore, taking this to be my Tx and this to be my Tf, I have a morphism. So therefore, there exists a morphism from here to here, such that T0 is P0t, T1 is P1t, and T2 is P2t. And indeed, one can show that this is unique. So there exists a unique morphism which makes this to commute. So this produces the uniqueness. Okay. Now let us have a look into another feature of this. Another viewpoint of this. So let me draw that picture again. So what do we have? We have Fp0 is partial 0 P1 and Gp2 is partial 1 P1. Okay. Remember the notion of a product category. Remember if we have two categories X and Y, we defined this product category which had these two projection functions. And if we had another category Z and functors Fg, R, PQ, then there exists a unique functor which is just this pair, which takes on the first coordinate it takes goes by p, and the second coordinate goes by q. Okay, so now we will come back to this. So let me rearrange these diagrams a little bit, and then we will come back. Okay. So now we can come back to this. So I have since there are these two functors, I have from the arrow category a functor into this product category. Okay. And also from this I have the functor here, which is f on the first coordinate and g on the second coordinate. Now let me look into this category. So from here again, since I have these two, I have P0 and P2, and over here I have my P1, and obviously if I start looking into the definitions of the functor, the composite of this is del 0 P1, del 1 P1, which by my thing is Fp0 and Gp2, which is nothing else but, if I look into the definition, this is nothing else but this. So this diagram commutes. Now suppose I have another, let's look into that universality again. Suppose I have another category. I have another category, X. And I have the functors as I have told. So this one commutes again. So del 0, del 1 T1 is nothing else but del 0 T1, del 1 T1. So this is equal to F cross G T0 T2, which means this is F T0 and G T2. So this means this actually provides us with the fact that del 0 T1 is F T0 and del 1 T1 is G T2. By what we have seen, it says that therefore there exists a unique functor such that this whole diagram commutes. So in other words, the universality can be expressed as another universality, and this is a very, very common diagram. We call this the pullback diagram. So this is the pullback. of along, or pullback of f cross g along. Okay, along the domain codomain plane. So that's my category. So before I finish up with this part, let's look into what is meant by a pullback more formally. So what is a pullback? So given the morphisms, we often say co-terminating morphisms. FMG, the pullback of F along G is triple. Let me say P0 and P1. So what is that triple about? So you have X and this, you have this triple where this is going to, and this is going to P1, such that Fp1 is equal to Gp0, and for any other triple with Ft1 is equal to Gt0. So for any other triple, there exists a unique morphism. There is a unique T from T to P such that T0, T is T0 and T1, T is T1. Okay. Obviously, as usual, show that the triple P, P0 or P1 is unique. So by this I mean unique up to a unique isomorphism. Okay, and hence we will henceforth write this as alternatively like this. Since this is y, we said x or y, so gf. Okay, and it's called the pullback. If we look into sets, pullback has a very nice description. So this is actually the set of all pairs yx in y cross x such that gy is equal to fx. So in other words, this is z over z, g inverse of z cross f inverse of z. So it's, you look into the fibers of g and f, so that's why it's called the fibered product. Pullback or the fibered product. So that's the notion of a pullback. So what we have shown is that f upon g is actually the fibered product of f cross g along the domain codomain theorem. Okay. Alright, so now we shall look into several examples. So we have now seen this category f over g, where we have the two functors f and just to recall, I'll just draw the diagram. So its objects are triples, diagrammatically they look like this. So actually they are triples, and its morphisms are pairs, such that we have this diagram. Okay. And then let us have a look into several examples of this. So the first one, we look into this. Now, most of the time, if we look into these diagrams, these objects, if we look into these, it gives us an idea of what this category is, and that is what we will do. So what is in this case? In this case, A, B, C are all the same categories, and F and G are the identity maps, identity functors. So what does the diagram look like? The diagram looks like this. Everything is happening in the category A. Alright, so objects are these horizontal rows, that means the morphisms, and the morphisms of this are this. So this is exactly nothing else but the category of arrows. So just to remind ourselves again that this is actually a pullback of the identity morphism, of the identity, right? F cross G over here is the identity, from identity to along the domain codomain, which is quite trivial, right? Okay, so just as a, so this is the pullback. Of the identity. functor along and this is a trivial. Okay, all right. I put forward another specific functor, which possibly I have also defined before. So, given any two categories, given the categories A and B, given the categories A and let's make this given the categories say X and Y, and an object, we have this functor which takes any object to that specific given object of Y, and therefore any morphism goes to the identity morphism of Y. Okay. This is usually denoted by delta Y, and it is called the constant functor. Okay. So the constant functor is the functor which takes every object from some category, from the domain category to that specific object. Okay. So now let us look into the second example of, say, F. Let's say identity A, and where T is a specific object. When I have taken identity A, it means F is actually identity A, so A and C are same. B can be anything, any category. I don't know what is it. So what are the objects? The objects then look like this. Well, this is happening in A, and we have, this is my object, and the morphism here it would be this. So in particular we can shorten this diagram to such triangles. So the objects are something like this, and the morphisms are such commutative triangles. This is usually called the category of bundles over T. And it is usually represented as this. Okay. A little bit of a digression on the name of bundles. Let A be sets, and we look, and T is a particular set, and we look into this category. So again, its objects are functions which go into this set, and this, and morphisms are this. Now let's try to have a picture. So this is my set T. I have the set A, the set B. Now, given a function, it gives me this bundle, right? And similarly another bundle over here. Okay. All right. So given this object T, I have this bundle. So this is coming from F. This is coming from G. So this is this bundle F inverse T. And this is this bundle G inverse of T. F is completely actually determined by this set of bundles as we vary our T over this set T. So functions are completely determined by those bundles, the picture over each element. And let us see what is this map doing. So what is this equation? This is telling me F is GU. So therefore, for any T, we know F inverse T is U inverse of G inverse of T. That means it actually says that this function U which you are taking, this function U is the demand of this commutativity is saying that it takes this, each such bundle is taken. So it is a peculiar function which kind of represents or preserves. So each members in these bundles are taken to corresponding bundles over here. So that's that function. So now this should make us clear that why the term bundle is used in an arbitrary category. We might think of this F as a bundle over T. Okay? We'll come back to this bundle. Later on. But let's continue with our examples. Right? So we have similarly, if we take the other way round, so this would be, so this is often called, this is the category of co-bundles. Over T. Okay. Good. Suppose now I take, before I go further away from this notion, well, let's take this. So what are its objects? Its objects are, they look like this. So the same thing, since this is the constant functor, we would have something like this. And this is Fe. Well, where now T is where T is an object in this. So you can say this F over T, but there is another name. We often say this as the cones. These are the cones. Cones over F, over cones of F. Cones, rather this cones below F with vertex T. Okay. And similarly we have where we don't call them cones, so its objects are the dual of this. So its objects look like this. It should be, sorry, it should be G in our notation as we were doing. So this should be GB. Then some other books, I should also mention this. In some other books, this is also called as if it is a kind of a sink. So it's called a sink with sink of F or an F sink. And this is also called, this would be called cones. So this is cones. Let me write it as cones from F. That's much better. So cones to G with vertex T. And the other one is F source. G source from. Okay. So these are several names. Now let us take a specific case when C is sets, okay, and let me look, T is a set, and let's take this, not a set, T is the singleton. Okay, so which is the, okay, which is the terminal object. I have not defined, so let me not put it like this here. let me write just as this. So then what is this? So its objects are as this is a set, again the same picture, but it is much more. Okay, but this means that F star is an element of GB. G star is an element of GC. And GV of B is therefore equal to C. Okay? So in other words, we have this, we can shorten this as by saying that the objects are, so the objects are pairs where B is an object of B and this is here, and on the other hand the morphisms where is a morphism of B and GV of B is equal to C. Okay? So this is often called the category of elements of J. Okay, and is usually denoted by this. So this is nothing else but the category of elements. Right? So this 6 examples tell us quite a bit about this special category of f over g. I will come back to this notion of this bundle again in the rest of this lecture. So the notion of the bundle. Firstly, we observe that this, in the special case of sets, a function f is completely determined by this family, which is a family of sets indexed by a particular set. Okay? So this brings us to another category, which is the category form of families of so what are its objects? Are families where AP is an object. And what are its morphisms? So we need this. So let's try and picture what should it be. So, well, we have objects. So here is this category of one family. Say this is one family. Say T is 1, 2, 3. And this is another family. Well, this is a strange thing. There is no such. So when I am considering this family, and there is another family. Say B1, say BA. So T is, so your S is A, B, C, D, and T is 1. Okay. So what I am trying to do is I'm trying to make a morphism over here. So the first thing would be to fix a map from T to S. Say 1 goes to C, 2 and 3 goes to B. And then once I fix this map, then I should somehow make a morphism, select morphisms from here to here, from A1 to BC, say F1, F2 is from, and this is also, okay, so F2 and F3 and F2 from A2 to BB, F3 from A3. So this is the picture, okay. So in other words, this is my study. Okay. So that means in general line it would be given by F and a family Ft, where, so formalizing this picture. Let me draw it here. Okay, so this is my isomorphisms are this, where f is a function and for each t ft okay, from 80 degrees, and that gives me the morphism. So what would be the compositions? Well, it's clear. So if I have AP from T to P, DS, SMS, and say CK from KK, I have F and this family. So what would be the composite? The composite would be GF. That's a map from T to K. Now let's see. If I take FT, it is from A. This is F. Okay. So AT to B of FT is my F. And G at FT goes from D of FT to C G of FT. So it is nothing else but G of FT composed with FT. So that's that family. Okay. And then I leave it to you to find out the identities, and that describes the category of families. Okay? So, let's take this, which is the category of family versus and for a fixed T, this is the category of families of A indexed by T. Before I come to this, let's fix this first. And then over here, so the indexing set is fixed, and we don't take so we take the identity map in particular and FT. So we just take the family. Okay, so the rest is alright. So, and we will look, this is family. Fam is the category of family of sets, and similarly fam T Now, let's see. I start off with this category of families of T, and I come and I look into this. So I'm going to produce two functors between these two categories. On the one hand, so what does I do? I take this object, so which is from here, I takes it to this family. And this object, so it goes to G university, and this morphism, well, this goes to UT. And what is UT? This is this morphism from F inverse T to G inverse T. X going inverse. That's exactly the commutativity condition which forces this. So this is the functor. What about the other side? I take a family and I am to give. So what do I take? I take the disjoint sum and which I call the map, say A. What does A do? A of say X T, this is A. Or why do I take A? Let me say it just reduces the second projection. By the way, remember what is this? This is nothing else but this union. Okay. All right. Similarly, so this is I didn't give a name to this functor. So this is say this is the projection. This is P, or let me say it's H. So this is this functor H. And then what is this? Perfectly. And this is U. Okay. And what is U? U of xt is UTX. Alright. Now observe. So these two are functors. These two are functors. But there is a very, very nice property of this term. Firstly, let's start off with A. So let's start off with a bundle. I apply I come here. Now this is exactly these are disjoint. So H, this disjoint union, is actually nothing else but this is, well, I cannot say. So this is but in this bundle, this is isomorphic. That means there is an isomorphism between this and A, which commutes over this. Okay? So there is an isomorphism in this category, in the category of bundles over here. On the other hand, if I go here, if I start off with a family, I apply H, I get to this. And if I apply I again to this, this is P2 inverse. This is P2 inverse of T. But P2 inverse of T is exactly P2. So I observe that I composed H is nothing else but the identity. Whereas H composed I is not the identity, but this is naturally isomorphic to the identity functor. So what is the story? They are not, the functors come and go back, they do not exactly produce in either way. In one way, if I start off with H and I come back, I start off with H and come back with I get back the same thing. But if I started off with I do not come back at the same place, but I arrive at a place which is isomorphic. So in the category of bundles, I cannot make any difference between these two objects. So the functors, two ways. Firstly, we cannot consider this as an isomorphism. So I or H is not an isomorphism. But if we look into it, that is not much of a difference. And since it is an isomorphism, properties, categorical properties, so properties intrinsic of the category of bundles over T, if one of it has, if this bundle has a property which is categorical, the same would happen with this bundle. So therefore, with this bundle, so therefore, it is very, very important that although they are not the same, their isomorphic categorical properties are not different. So we shouldn't actually consider this to be really different. See, although it is exactly not the identity, it is somewhat very much close to it. And a situation like this, we shall come back later on to call it an equivalence of categories. So the categories of families with the same vertex T, with a given vertex T, is equivalent to the category of bundles over the set. We get back again to that notion of an over category, but in another special case. The special case is when I have a pair of functors between A and B. A and C. Well, in this case, again, we have this category. We have these functors. And with its. Now I take a very, very special case. So I take a functor, which is the identity functor on A, and the identity functor here and a functor here with the property that partial 0 R is F and partial 1 R is G. Then I know that there exists this exactly is giving me that unique functor with this. But let us see. What is this? Giving such a thing, therefore, I am giving so each object A goes to a morphism. And what is the, again by what we have done, the domain of it is FA and the codomain of it is GA. So, anamorphism F will go to a pair. And what is that pair? The domain of it I know is F of F and the codomain of it is G of F. So it is F of F and this diagram commutes. So in other words, giving such a functor F, giving such a functor R is the same thing as giving a natural transformation. Okay? And what does this tell us? So giving a natural transformation alpha is same as giving such a functor, which means that I am actually giving a functor from A to the category of F upon G, and hence the notion of a natural transformation can be seen as a special case of a functor. Okay.